question that naturally arises when we collect and analyse data is whether there is some relationship present in the data that's been collected. When we collect bivariate data, we might ask questions like, is there an association between the two variables? We might wonder, is it just the group that we've investigated, or if it's the sample and not the whole population? We might think, is this what we observed really that unusual? Many statistical tests exist to answer questions like these. The chi-squared test, written like this, is the test that we use to look for associations between variables when we have bivariate categorical data. While looking at percentaged frequency tables can be one way to try to see if there may be an association between variables, the chi-squared test offers us a statistical test to look for the relationship between two categorical variables. The test works by first assuming that no relationship exists. Then we generate what the expected data should look like. Next, the observations are compared with those expectations. And finally, distribution is used to ask exactly how different are the observations and expectations. A natural question to ask is exactly how does this method compare between the observed and expected data? It turns out that under the assumption of independence, our samples should look a certain way, and that kind of makes sense. We calculate a measure of relative difference, given here, which is called the chi-squared statistic. Under the assumption of independence, this chi-squared statistic should in some sense be small in value. But from sample to sample, the chi-squared statistic will be different. For most samples, if the variables truly are independent, then the chi-squared statistic should be quite small. Very rarely would it take on a large value. This graph in the bottom left shows us the situation that we should expect for chi-squared values for 2x2 bivariate categorical data. What the graph means is that for most samples, the chi-squared value should be quite small. In fact, we'd expect to be getting most of the values less than 2, certainly a lot of them less than 3, and hardly any of them out here bigger than 6. When we're trying to test if the variables that we have collected data on actually are related in some way, in other words are not independent, we determine what the chi-squared statistic is for our sample, and then see how likely it is that that chi-squared statistic could be observed if the variables really are independent. For example, if we received a chi-squared statistic of 7, we can see that it's very, very unlikely, looking at this graph and the area beneath the yellow line, that values bigger than 6 would be observed for the chi-squared statistic under the assumption of independence. We might then conclude that it's pretty unlikely that we would get that chi-squared value if the variables really are independent. On the other hand, if we had another example where our sample showed a chi-squared statistic of 1, we might say that it's fairly likely that we could get values of 1 or bigger as our chi-squared statistic under the assumption of independence. We can't really say much then, other than that we're not going to throw away our assumption. Let's take a look at an example. The table at the top shows some data that's been collected that's bivariate and categorical in nature. It talks about the type of school that a teacher belongs to or works at, and whether they use social media for professional reasons. We can see, for example, that there are 19 teachers who work at independent schools who do not use professional social media, and so on. We could create a percentaged version of this table and find that, for example, 58 out of 82, or 70.7% of public school teachers do not use social media for work purposes. And might then be wondering, is there a relationship between the school system that the teacher works at and the use of social media for work? This is exactly the kind of situation that we can investigate with a chi-squared test. We'll carry out the test by first determining what the expected frequencies would be in our two-way table under the assumption that the two variables are independent. We'll then use that to calculate the chi-squared statistic, and finally compare that chi-squared statistic value with the chi-squared distribution and make a conclusion with regards to our question. Assuming that there's no relationship, in other words, that the two variables are independent, then each cell value in our table of expected frequencies should be proportional to the total number for each of the defining characteristics or variables. For example, the number of public school teachers who do use professional social media should be proportional to the total number of public school teachers and the total number of teachers who use social media professionally. In other words, we want to multiply 82, the total number of public school teachers, by 47, the total number of teachers who use social media for professional reasons, and then divide by 124, the total number of teachers altogether in the sample. This gives us an expected frequency of 31.1. For public school teachers who do not use social media for professional purposes, we'd expect 82 multiplied by 77 this time, divided by 124. The change being that we're looking at the total number of teachers who don't use social media professionally. This calculation gives us 50.9 for our expected frequency. Notice again that when we add up across the row, we still get the same total, marginal total, as we did in the original table. And this should occur for all of the rows and all of the columns. Pause the video now and try to fill in the two remaining cells for yourself. Then finish off the table by filling in the marginal totals and the overall total. After filling those in myself, I've got 15.9 and 26.1, and then just went through and checked that my marginals and totals all added up as they should do, exactly the same as they are in the original table. Now that we have our expected frequencies and the observations from the beginning, we can go ahead and calculate our chi-squared statistic. The chi-squared statistic is given by this formula, and it reads like this. Chi-squared is equal to the sum from I equals 1 to 4, because we have 4 cells in our two-way table, of observation I minus expected frequency I, all squared, divided by expected frequency I. So in other words, we'll be looking at corresponding values in the expected and observed two-way tables, subtracting them, squaring the values, then dividing by the corresponding expected value, and adding those up for each cell in our two-way table. The first one, for example, would be public school teachers who do use social media for professional reasons. In this case, the observation is 24 teachers. The expectation is going to be minus 31.1. These are just the first cells in our two-way tables. We need to square that and then divide by that expected value again. Pause now and see if you can follow the same pattern to fill in the 3 remaining values in our chi-squared statistic. I've gone ahead and done that and obtained the following 3 values. Now doing that on your calculator, you should end up with something around about 7.67. So our chi-squared statistic for this observed data is 7.67. But what exactly does that mean? Is that a small chi-squared value, or is that a big chi-squared value? After all, we're trying to figure out if our chi-squared value is so big that it's really unlikely to happen if we have independent variables in our data. Well, the way that we figure that out is to go back to our picture of the distribution. Remember that we said that values bigger than 6 look to be really unlikely to happen. There's hardly any area under the curve there. So it's really unlikely that a value of chi-squared bigger than or equal to 6 is going to occur. Whereas a value bigger than or equal to, say, 1, there's quite a bit of density under the curve there. So that could quite likely happen. Given that our chi-squared statistic is 7.67, it looks like that's fairly unusual. A more definitive way to look at this is to look at a chi-squared distribution table. Now this is actually just taken from the graph anyway, but what it does is it gives us some neat cut-off values to compare our chi-squared statistic to. In our situation, where we have a 2 by 2 two-way table, we're talking about 1 degree of freedom in our chi-squared distribution. What this table tells us is the probability of a larger value of chi-squared given the chi-squared values which are written inside the table. So for example, a value of 6.63 for your chi-squared, then the probability of having a larger value of chi-squared than that is 0.01 or 1%, a very small amount. Now looking at our chi-squared value, 7.67, that's even bigger than 6.63. So the probability of a value of chi-squared larger than 7.67 is even smaller than 0.01. So it's very, very unlikely that we're going to get that if our variables really are independent, as we assumed. So what we're going to do because of this is we'll reject our assumption. The chi-squared statistic we've calculated means that the data we've collected, the observations we've made, suggest that there is a relationship between the type of school that the teacher works at and whether they use social media for professional purposes.